So, in the last class we discussed the electroacoustic analogy, and we also had some discussion about this source impedance. So, here was the equivalent circuit that we had derived. So, here we had done the source modeling. The source was this P n plus 1. So, this is like saying that the source is a constant voltage source, but then that it goes through a source impedance and then reaches the load, right. So, this is what is called the Norton's circuit analogy. A completely equivalent picture is brought about by the Thevenin circuit analogy, which is what we will touch upon now. So, this is wherein the source is modeled as a voltage source, and then there is a source impedance ZS or Z source, if you might call it, and then there is a load. Okay. So, this load will include both the muffler as well as the radiation impedance. So, this part, if you like, is the load. Okay. So, I am just redrawing this picture by collating the muffler impedance together with the radiation impedance and calling it as the load impedance. So, in here what you will have is that though the source is supposedly working at a voltage of P n plus 1, but what reaches the load is not P n plus 1. This is P n, which is different from P n plus 1, because there is a source impedance which is connected to it. So, to calculate what is the value of this P n, we are doing this simple calculation. So, firstly we understand that the current that is flowing through the circuit V n plus 1 is P n plus 1 divided by plus Z load, right. So, therefore, P n is P n plus 1 minus Z source into V n plus 1, which is also equals to V n, because between the input and the output terminals of the source impedance there is no fall in current, that source impedance is in line, right, it is not in the shunt position. So, therefore, you could as well write this as P n equals to P n plus 1 minus Z so into P n plus 1 divided by Z source plus Z load. Okay. Now, we want to have another equivalent picture which will assume that we have a constant current source V n plus 1 to denote the current source. This is a constant current source, and this current source is acting over the load, but this time since I am modeling the source as a current source rather than a voltage source, I have to give the source impedance in parallel. Okay. So, let us see what this reveals, and again we have the load impedance here, right. So, here the V n plus 1 will get split into two parts. One is V n. So, V n plus 1 and V n will not be same in this situation, because a part of the current will move in this shunt line, which will be of the form V n plus 1 minus V n, right. So, if this is again P n, okay, because we want this P n to be the same, we want to have an analogy between these two circuits, and what we will show that if V n plus 1 is chosen as P n plus 1 divided by Z source, then we will have then the analogy is complete. The analogy between the two source models, one in which we are modeling the source as a voltage source, or in acoustic terms as a pressure source, and the other in which we are modeling the source as a velocity source, or in electrical terms as a current source. Okay. So, let us see what our electrical modeling this time will give us. It will give us that V n plus 1 minus V n into Z source must be equals to P n, right. So, in other words, V n plus 1 into Z source minus V n into Z source must be equals to P n, or the terminal voltage across these two ends. So, here what we have is V n plus 1 Z source will be again P n plus 1 as per the definition. So, P n plus 1 minus Z source into V n should be equals to P n, and here in this circuit we had V n plus 1 to be the same as V n itself. This is about, please understand, the two circuits are different. So, in this circuit we had V n plus 1 is equals to V n. So, we could replace V n plus 1 here as minus Z source into V n. Now, note that these two equations are exactly reading out to be the same, with the condition that I have chosen my current source to be equal to the voltage source divided by the source impedance. So, these two forms of source modeling are perfectly equivalent both in the electrical community as well as now that we are talking about electromechanical acoustic community, we will exploit this analogy of source modeling to give us better insights into how a muffler can be better designed. So, the point is this, that if this condition V n plus 1 is equals to P n plus 1 divided by Z source is invoked, then we get to see that the current, by applying the circuit laws in this second circuit, we are getting the same equation. These two equations are identical, right, which means that the two equations the two circuits are completely equivalent. So, therefore, the velocity modeling of the source in our electromechanical system would read in this following form. You will have a velocity source V n plus 1, and then you will have a source impedance which is in the shunt position. Then you will have the muffler which could have elements in the inline position, which could have the elements in the shunt position, and finally, you will have the radiation impedance Z0, right. So, this is the circuit when you do the modeling in terms of velocity source, whereas what was shown earlier here is the circuit in terms of the source modeling taken as a pressure source. Okay. But both has its advantage. For example, if the source impedance is near 0, then what is happening is that the entire source voltage or the source pressure is getting communicated downstream, whereas if the source, so in other words, if the source impedance is approaching 0, then this circuit is getting shorted, right. So, if we wish to study the situation where source impedance is very low, then you can have this circuit to your help, because that will be easier to interpret, whereas the interpretation for a very large source impedance can possibly be better with this modeling, because when the source impedance is very large, this will be made an open circuit. See, this will be a current source with an open circuit in the shunt position, and that will have a very interesting special cases. But special cases apart, let us now try to define insertion loss, which is a very important aspect in muffler design. So, insertion loss, you consider two cases. Case 1, when you have only the source, and I am going to draw only the circuit here. You have only the source, you have the source impedance and you are having the radiation impedance for sure, Z0, right. And in case 2, I will call Z source as Zn plus 1 because that will simplify my nomenclature. Zn plus 1 is the source impedance. So, Zn plus 1 equals to Z source. Okay. And case 2, wherein we will have a current source Vn plus 1, a source impedance which is in the shunt position, and then you have the impedance associated with the muffler and the inlet and exhaust pipes. So, impedance of inlet, pipe, muffler and tailpipe, all of it goes in this box, and finally it comes out through the radiation impedance. In these two cases we need to evaluate the two sound powers, W1 and W2. Sound power in case 1 and sound power in case 2 has to be evaluated, and then the difference between the two needs to be calculated for the insertion loss idea, because this, as I said, is the real benchmark of how effective your muffler arrangement is. If you do not give any muffler or anything, it will have the value of the sound radiated to be W1. If you give a muffler, it has the value of the sound radiated to be sound power radiated to be W2, right. The difference between the two is the insertion loss, which is basically the benefit that you are getting by inserting the muffler together with its inlet and exhaust. So, that is the measure of the effectiveness of the exhaust system in terms of acoustic performance. Okay. So, here for W2 we know that if V0 is the current that was flowing through the final load resistance, we have already derived this expression that W will be 1 by 2 rho V0 square into R0, right. So, this expression was already derived 1 by 2 rho mod of V0 square R0. R0 is the resistance associated with the radiation impedance value. The radiation impedance has reactance as well as resistance. We only care about the resistance, we do not care about the reactance while calculating the sound power, because it is the time averaged power that is radiated out. Okay. Here also it is just the same, but the point is the V0 here, even if the Vn plus 1 in both these cases is the same, because the source is obviously the same. Even if the source is the same, the amount of V0 which goes through the impedance block Z0 is going to be different. So, here it will be V0 prime, right. So, W1 will be 1 by 2 rho V0 prime square R0. Okay. Please understand that Vn plus 1 between the two system is same. In the two cases is the same, because it represents the same source. Zn plus is the same, Z0 is the same, right, between case 1 and case 2. But V0 obviously will be different, because the amount of current which actually passes through the Z0 impedance will be different depending upon what circuit you have in this block. So, therefore, V0 prime we have to keep track of it. So, now what we will do as a final reduction process is that we will try to relate V0 prime in terms of Vn prime. That should be trivial from the circuit analysis perspective. This is Vn plus 1, this is Zn plus 1, and this is Z0. Okay. And we know that this is V0 prime, this is Vn plus 1. So, what goes here is also V0 prime. So, what goes here is Vn plus 1 minus V0 prime, right. So, Vn plus 1 minus V 0 prime into Z n plus 1 is the potential drop across the first shunt, across the impedance Z n plus 1, and that potential drop has to be matched with V 0 prime Z 0. So, this is the potential drop across this position, right, across the impedance Z 0. So, therefore, what you have is V n plus 1 Z n plus 1 is equals to V 0 prime Z 0 plus Z n plus 1, and finally, V 0 prime is equals to V n plus 1 divided by Z 0 plus Z n plus 1 into Z n plus 1, right. So, therefore, W 1, which was the sound power which is radiated in the situation where there is no muffler, no inlet pipe, no tailpipe, nothing of that sort. So, W 1 was given as 1 by 2 rho V 0 prime square R 0, and V 0 prime we wish to now write it as 1 by 2 rho V n plus 1 whole square divided by mod of Z 0 plus Z n plus 1 whole square mod of Z n plus 1 whole square. Okay. So, this is the expression for the sound power that is radiated. This is the sound power radiated in the linear scale. We will come to the log scale soon enough, but this is just the sound power that is radiated or power that is lost in the circuit into R 0, yeah, into R 0 I have missed out. So, this is the sound power that is radiated in the case where there is no muffler, and W 2 is going to be anyway 1 by 2 rho mod V 0 square R 0. Then what we have to do is we have to find the sound power in the logarithmic scale. So, that should be easy. Sound power in the logarithmic scale, as we know, is 10 log base 10 W 1 by W reference value, and similarly L W 2 is going to be 10 times log base 10 W 2 by W ref. So, therefore, the insertion loss is going to be L W 1 minus L W 2, which is 10 log 10 W 1 by W 2, and then if we put the appropriate values now which we have calculated for W 1 and W 2, it reads in the following fashion. The R 0 term now you see actually does not affect the insertion loss. The R 0 term you see is going to get cancelled from both the numerator and the denominator in that ratio. What we will be left with is Z n plus 1 divided by Z 0 plus Z n plus 1 magnitude square into V n plus 1 divided by V 0 magnitude square. This is the insertion loss formula, right. Now, obviously, Z n plus 1 and Z 0 are sort of something for which you do not have any control. Z 0 is the radiation impedance, it is God given, you have to just accept it. Similarly, source impedance depends upon the mechanical or the fluid dynamic properties of the source, you cannot change it. So, the only way in which you can change the insertion loss to your benefit is to look at this ratio of V n plus 1 V 0. Let us understand what is this ratio V n plus 1 by V 0. So, if you look at this circuit diagram, it is very clear that from the current at the source, which is V n plus 1, only a part of this will be able to reach the load which is of the value V 0. So, if you have some lines which are in the parallel position and divert the current not towards Z 0, but towards the other parallel bypass lines, then you will achieve a very large reduction of V 0 with respect to V n plus 1. So, this ratio is of critical importance. The ratio V n plus 1 divided by V 0 is called the velocity ratio and is a fundamental factor in determining the insertion loss. Okay. And insertion loss, as I said, it is just the benefit that you get by addition of your exhaust system. If you do not have an exhaust system and you let the source directly radiate out into the atmosphere, then you will get a sound power radiated as W1, and on the other side it is W2 if you have an exhaust system. If you just take a difference between these two sound powers in the logarithmic scale, this is what is insertion loss. So, insertion loss is the true benchmark for the performance of the acoustic performance of your exhaust system. So, what it turns out here, from here what it turns out is the following: you have to have some bypass paths in this block such that most of the current does not flow through this path, right. You have to reduce V0 for a certain value of Vn plus 1. How can you do that? If you have a certain, within this block, if you have a short circuit path, let us say, that will be ideal. If you have a short circuit path of this sort, what will happen? Then the entire current will go through this short circuit path and minimal current will actually go through the the radiation impedance Z0, and therefore V0 will be drastically less, and Vn plus 1 and V0, that ratio will be very high, insertion loss will be very high. So, that is how we should go about trying to design for good insertion loss for a muffler, right. Sometimes the problem is you will not have in your table the knowledge of the source impedance, because let us say you are a vendor for just the muffler component and there is no way that you know the source impedance, in which case transmission loss may be sort of the best approximation that you can do to benchmark your mufflers. But once you know that this muffler has to be fitted with a particular source, then you must always calculate the insertion loss, and to choose the best muffler for a given source you must do the insertion loss calculation. Unless you do the insertion loss calculation based on transmission loss, the exercise could go completely futile. Okay. So, let us quickly illustrate how you can create a bypass path. So, suppose now we have an exhaust system which is this form. So, what I have done is I have put a Helmholtz resonator on my exhaust pipe. So, what is going to happen here? So, here I have an incoming velocity, I mean acoustic velocity V3, and here there is an outgoing acoustic velocity V1, and here there is also an outgoing acoustic velocity V2, right. So, applying conservation of mass flow at this junction point, we get V3 is equals to V1 plus V2, right. What about the pressures? Because all these points are continuous, all the points will have the same pressures, P1 equals to P2 is equals to P3, right. So, now if this is so, then what we can write is V3 by P3 has to be equals to V1 by P1 plus V2 by P2. Okay. If we call the impedance P3 by V3 as zeta 3, okay, then this can be written as 1 by zeta 3. Similarly, if we call P1 by V1 impedance as zeta 1, then we could write this as zeta 1, and finally, if we call P2 by V2 as the impedance Z2, then we could write this as Z2, 1 by Z2. So, in this situation we are going to have, if you just look at what happens upstream point of the Helmholtz resonator and what happens at the downstream point of the Helmholtz resonator, you are going to find that V3 is going to get bifurcated or subdivided into two parts, right, and V3 stands for the current, the velocity stands for the current in our analogy. So, the current is going to get divided, the voltages are going to remain same, which is the pressures, and the impedance that you are now seeing is effectively that of the equivalent circuit of in which the you have parallel impedances in parallel, right. So, the equivalent circuit for this case would be as simple as this. You have one impedance Z2 which is in parallel, and this impedance is zeta 3 and this impedance is zeta 1. So, zeta 3 impedance can be recovered from zeta 1 impedance and from Z2 by simply appealing to the impedance of two parallel circuits, right. And with this, again what you can find out is that if the Z2 impedance, and what is the Z2 impedance? Z2 impedance is exactly the impedance of the Helmholtz resonator, because V2 is exactly the impedance at the inlet of the Helmholtz resonator, right. So, if the impedance of the Helmholtz resonator goes to 0, what will happen? This path will be short circuited, right. So, this is the circuit of only this portion. Now, if I add a source, so in the next picture I will add a source and I will add a Helmholtz resonator and a tailpipe which opens into the open atmosphere, right. So, this is the source and this is the Helmholtz resonator. So, what will happen here? The equivalent electrical circuit will read in the following fashion. You have a Vn plus 1 associated with the source, you have a Zn plus 1 associated with the source impedance, you have a certain tailpipe, an inlet pipe. So, this is the impedance associated with the inlet pipe, and remember the pipe impedance we have discussed in the form of, the pipe modeling we have done it in the form of transfer matrix. In general, it is neither in shunt position nor in inline position, it is a distributed impedance. So, we should not put the impedance associated with the inlet pipe in either inline position or shunt position, but we may put it in this form to denote that it is a distributed impedance, something which cannot be put in the two extreme cases. Then we should have a Helmholtz resonator, and the Helmholtz resonator will be in parallel as we have discussed. So, this I will call as ZHEL associated with Z Helmholtz, and then you will have the tailpipe. This is the tailpipe, this is the tailpipe, this is the inlet pipe, and that is the Helmholtz resonator, and finally it has to open to a radiation impedance Z0, right. Now, the point is this, that out of all these, if you know that you are hearing a large sound at particular frequencies, then what should you do? You should tune the Helmholtz resonator. Remember, the Helmholtz resonator has a resonance frequency, we have described that. The mass effect is there, the spring effect is there, one of it is V by C square, the other of it is L by S. You can tune the frequencies associated with this Helmholtz resonator such that the problematic frequencies are exactly the resonance frequencies of your Helmholtz resonator. In that case, what happens? If the frequency happens to be the resonance frequency of the Helmholtz resonator, what will happen? This part of the circuit will show 0 impedance, right. 0 impedance is the situation where you have resonance frequency. Once you have resonance frequency, this impedance will turn 0, and then it will be replaced by a short circuit line. And then in the electrical terminology now, it is very easy to understand, once this line is shorted, most of the current will flow through this line, it will not prefer to go anywhere else, right. And as a result, the V0 which passes through, remember your ultimate objective is to minimize V0. That V0 will get minimized.
Here we are tuning the Helmholtz resonator for only one frequency.
Yes.
So the rest of the frequencies will still pass.
Yes. This is, I have now killed one, the most problematic frequency. In my frequency spectrum, I would see that there are lots of frequencies which are contributing, right, but I can always find out which is the most dominant frequency contributor, right. I will kill one with one Helmholtz resonator. Now if I have multiple frequencies, I will use multiple Helmholtz resonators. I can give as many Helmholtz resonators as I want in this pipe and start knocking off each of these frequencies. It is a very scientific method that at least you understand that, you understand how you can knock off one, right. If you know how you can knock off one, you can knock off the others also by using a similar strategy for all the other frequencies. But the point I wish to drive home with this electromechanical analogy, which is very difficult to do by staying in mechanical systems or even in acoustic systems, is that this idea of shorting the line. The Helmholtz resonator is actually providing a short circuit to the equivalent electrical system and thereby saving the current to go into the radiation impedance.
What enters the Helmholtz resonator, is it coming back into the circuit?
No, all that is taken care of. See, what we are saying is that from here on, what goes ahead is, in that terminology we had said V1, and what goes here is V3, and what goes here is, sorry, this is V2 and this is V3, right. So from here on, what goes from downstream of the Helmholtz resonator is only V1, right. Downstream of the Helmholtz resonator, this in the previous diagram, if you see, downstream of the Helmholtz resonator is V1. See, here what is happening is a standing wave is getting generated. It is not that it is only a travelling wave and it will get reflected. A standing wave situation has already created, that is why it is a resonator, right. Otherwise you cannot have a resonator. A standing wave situation has created. It is only that now we are appealing to the impedance of the Helmholtz resonator and we are tuning the resonance frequencies such that you have a zero impedance in the bypass line. Okay. Thus, to reduce V0 at a particular frequency, we need to tune the Helmholtz resonator such that its resonance frequency coincides with this frequency. Okay. This tuning can be achieved by appropriately choosing the volume or the length of the resonator. Okay. So, I think just one more note I will do before I go today, that is at the resonance frequency, the impedance of the Helmholtz resonator goes to 0, thus providing a bypass line in the electric circuit. and achieving minimal V0. So, if your V0 is minimized, velocity ratio will be increased and your insertion loss will increase. So, that is the demonstration of the insertion loss of again a pretty much academic muffler I would say, but quickly in the next class we will show some practical construction where this idea of a Helmholtz resonator will get nicely approximated. Okay. So, till then goodbye.